Proportions and similarity. Now we just finished talking about congruent figures, and remember that congruent figures were same shape, same size. Now we're going to be talking about similar figures. Similar figures are not the same as congruent figures. There are some congruent parts, but we're going to see what those are as we move through the lesson today. What is similarity? Bear and a monkey, not similar. Two butterflies. One looks just larger, but almost an exact replica shape size of the other. That's similar. Two triangles. Similar. Two polygons. Well, both of them are polygons, not similar. Similar figures are figures that have the same shape but not necessarily the same size. But what does same shape mean? Are the two heads to the right similar? No, they're not similar. While they are both faces of a guy, one has been stretched vertically, one has been stretched horizontally, and as such, we have not created similar shapes. Similar shapes are proportional in size. Now, how does this differ from congruence? Congruent shapes are identical in size. Remember, we talked about congruent shapes being transformations that result in congruent shapes are translations and rotations and reflections. Our similar figures are our dilations, objects that get larger or smaller based on a consistent scale factor. That means these shapes cannot be horizontally stretched or vertically stretched. Similar figures cannot be horizontally shrunk or vertically shrunk. Similar figures can be thought of as enlargements or reductions with no irregular distortions. So two figures are similar if one can be enlarged or reduced to make it congruent to the other. Similar triangles. When triangles have the same shape but may be different in size, they are called similar triangles. We express similarity using the symbol that looks like this. Notice we've seen that before. We saw that as part of our congruency statement. So our congruency statement is basically saying we are similar and exact. The similarity symbol is basically just saying that these shapes are similar. They are proportionate in size. So triangle ABC is proportionate in size to triangle PRS. An example. Triangle 1 is similar to triangle 2. Are they the same size? No. Triangle 1 is smaller than triangle 2. But they are similar. Notice that triangle 1 on the right is not similar to triangle 3. While it's true that they are both triangles, they are not the same shape triangle. One is an isosceles triangle and the other is a right triangle. And so we have to pay attention to make sure that they are identical in shape and then either scaled down or scaled up based on the scale factor. So, similar figures are proportionate. Notice that we see AB is proportionate or has a ratio equivalence to ED. Now, every side on our shape is going to have the same ratio. So AB to DE is one ratio. BC to EF is going to have the exact same ratio. AC to DF will have the exact same ratio. Now, you will notice that the angles, however, are congruent. So while a congruent shape has same shape, same size, a similar figure has the same shape but different size, and it has different side lengths but congruent angles. Different side lengths but congruent angles. When stating that figures are similar, use the symbol for similarity. For the triangles above, you can write that triangle ABC is similar to triangle DEF. Again, just as we talked about last week, make sure that corresponding vertices are in the same order. It would be incorrect to say that triangle ABC is similar to triangle EFD, because then we would be saying that A corresponds to E and it does not. A corresponds to D, and thus the angle A and angle D are congruent. Angle B and angle E are congruent. You can use proportions to find missing lengths in similar figures. Now, this is where we tend to see the geometry used when we're dealing with similar and congruent figures. So if triangle ABC and triangle RST, we want to list all of the pair of congruent angles and write a proportional relationship that relates corresponding sides. So from our statement, we can see that A and R are congruent. So we would say angle A is congruent with angle R. We could say that angle B is congruent with angle S. And we could say that angle C is congruent with angle T. That is the only part of these shapes that is congruent, is the angles. The sides are proportional to one another. So generally I work with my statement and I would start with my first two letters. AB is proportional to RS in the same way that BC is proportional to ST. In the same way that CA is proportional to TR. And so now we have a proportional statement that relates the corresponding sides. All right. So we have a similarity statement. The similarity statement allows us to identify all of the angles that are similar. Now let's try some examples where we are using those proportional relationships. So notice we've got two similar shapes, and since the side lengths are proportional, we can write a ratio of this side to this side, and we can write a ratio of this side to this side. Now, one of the things we want to remember about writing ratios is we typically write words first. And I'm going to go ahead and tell you that is a really good strategy towards making sure that you set up any problem correctly. So I'm going to write words first. Small triangle, right side. Big triangle, right side. So I need a 4 over a 6 Now, I have a small triangle in the numerator. I've got to have a small triangle in my other ratio. Numerator, left side. Which means I will have a big triangle in my denominator, left side. So my small triangle on the left side of the shape, we have the x. My big triangle on the left side of the shape, we have the 4.5. And we should remember that anytime we have a proportion, we can solve by cross multiplying. So we want to multiply 4 times 4.5 gives us 18 is equal to 6x. Which now we have a one-step equation, so we can divide by 6 on both sides, and x is equal to 3. So we now know that this missing side length over here is the other one. In the figure, the two triangles are similar. What is the length of C? Now, you will notice that I've given some arc angles, so arcs in the angles. Now, I did these with PowerPoint. PowerPoint wasn't making little curves when I first created this. I haven't gone back and edited it. You do tend to see the arcs as curves, but that's okay. We understand one line to one line, two line to two line. Now, what the two lines and the one lines do is they give us a sense of direction. So if I go from the angle that has one line to the angle that has two lines, we can start putting together some corresponding parts. So I have gone from triangle A, C, B, one line to two line, is similar to triangle one line to two line. So we can see our corresponding parts now. Triangle P, Q, R. Now that I know my corresponding parts, I know what sides are corresponding to one another. So we can start setting up a proportional relationship. So I can see that AB is proportionate to PR. And so I could tell myself the big left to the small. Actually, let's do this. Let's call that big longest side because that appears to be the longest one, to the small longest side. That way we're keeping our wording consistent. So now we want C, which is our middle, big shape middle side, is going to correspond with the 4 small shape middle side. And again, how do we solve any proportion? We cross multiply. So 10 times 4 is 40. 5 times C is 5C. And we have a one-step equation where we divide by 5 on both sides, and C is 8. So we've now determined that this side length that is missing is 8. Now what about the length of D? Again, since we're dealing with the same triangle, we're just going to set up for proportion. So we can still use the 10 over 5 because that ratio is still going to be consistent. But now notice we're using the 6 corresponds with side D. Again, we cross multiply, divide by 10, and our value of D is 3. Setting up proportional relationships with angles is very, very common. So let's see how it's used in real life. Suppose that you want to find the height of this tree. Unfortunately, all you have is a tape measure, and you're too short to reach the top of the tree. You can, however, measure the length of the tree's shadow. You also can measure your own shadow. Take just a minute if you can start to figure out how you might be able to find the height of the tree. All right, welcome back. Now, if you haven't seen it already, notice the height of the tree is here. The shadow extends here. If we connect the two ends of those lines, what kind of shape are we ending up with? Your height extends here. Your shadow extends here. We connect the two lines again. Lo and behold, we have a 2-foot shadow, a 6-foot person. We have a 10-foot shadow and an unknown height of the tree. All right. Since we would assume that the sun is somewhere up here shining its rays down, it is going to cast a shadow where we would end up with equivalent angles here. We would end up with equivalent angles. Sorry, that's a right angle. And we would end up with equivalent angles up here. Which means we're dealing with two similar triangles. Obviously, they're not the same size. One has a shadow of 2 feet. The other has a shadow of 10 feet. Since they are similar triangles, we can set up a proportion. So notice the height of the tree over 10 is equal to the 6, the height of the person over his shadow. Now this is a slightly different way of setting up the same type of ratio proportion. Traditionally, I would have you say the height over the height is equal to the shadow over the shadow. Now what you will notice is that as long as we're keeping our corresponding parts equivalent and putting them together in the same ratios, when we cross multiply, notice what happens. H times 2, H times 2. So it hasn't really changed how we're solving the problem. This is just a different perspective on how to set up the problem. The ratio of one side to its second side is equal to the ratio of one side to its second side, as long as we are keeping our ratio consistent with the corresponding parts. So notice I did the ratio of the left side to the ratio of the bottom. With the person, we did the ratio of the left side to the person of the bottom. That is fine. Again, we solve by cross multiplying. 2 times h, 6 times 10. And then we divide by 2 on both sides and determine that the height of the tree is approximately 30. Let's try it again. When a 6-foot student casts a 17-foot shadow, a tree casts a shadow that is 102 feet long. Find the height of the tree. Now, anytime you have triangles inside triangles, you're going to tend to have similar figures. Because notice, I have got two triangles that are sharing the same angle. I have got two right angles, and then this line up here that is extending from this top point to this bottom point is functioning like a transversal. Notice I can draw that line straight up. I can draw this line straight up. Since they are perpendicular to this bottom line, right angles, then that means these two lines sticking straight up are parallel. So I have a corresponding angle that would be congruent. Notice how we're pulling in more than just similarity into this unit. We're bringing in corresponding angles from our parallel lines proofs. All right. So we now know that we're dealing with similar triangles. Since we're dealing with similar triangles, we can write a ratio of the parts. So I could say something like the height of the tree over the height of the person is going to be similar or proportionate to the shadow of the tree over the shadow of the person. And at this point, we cross multiply. 17 is equal to, 17h is equal to 6 times 102, which is going to be 612. Now we want to divide both sides by 17. And h is equal to 36. We said feet. 36 feet. Hopefully that helps you to understand a little bit more about similarity today. You should be able to use this information to work on the assignment sheets that were assigned. Have a wonderful day.